In this video, we are going to look at operation of a cyclotron. A cyclotron is a particle accelerator. So basically, as the name suggests, it is used to accelerate particles. Particle accelerators are needed when you want to conduct nuclear research, and they're also needed if you want to smash atoms and create radioisotopes, which are used in medical industry for diagnostics. Now, if you look at linear accelerators, so for example, you want to accelerate an electron from here, what would you do is you would put rings here and you put them in a sequence, so that and with each succeeding ring at a higher voltage than the previous one. So for example, this ring could be at 100 volt, this ring could be at 200 volt, this could be at 300 volt, could be 400 volt, and so on. So this 100 volt means it is at some higher, it is positively charged. 200 volt means this ring is more positively charged. This is even more, and that's even more. So electron, when you launch an electron here, this electron first gets attracted towards this 100 volt ring. It passes through. When it crosses the first string, it can see a higher, more positive charge here, so it gets accelerated again, and that's how it keeps on going. And what we have is a electron beam here, which would have some velocity. So these kind of accelerators, basically they are linear, and if you want to use this kind of accelerator, then you need to have it in a very linear manner. Linear means you need to have that in a straight line, and that line at times can be very long. So some particle accelerators are of the length 2 kilometers, 3 kilometers as well. These kind of particle accelerators, they are very costly to set up, because you want to make such a long tunnel, and then you need to evacuate. There should not be any air molecule there, because you got air molecules, the electrons would hit the air molecule, and the whole purpose of accelerating the electron and getting the accelerated electron here would be lost. In a cyclotron, what we do is, let me first clear this thing. We don't need this diagram anymore. In cyclotron, we use the fact that a charged particle moves in a circular path when it is moving in a magnetic field. So we use that concept, and we make the electron go around in circles instead of going in a straight line for kilometers. We make the particle move in a circular motion, and we accelerate it at the same time, so that when it comes out, we have accelerated beam, and because it has traveled in circles, it is the size of the cyclotron is normally small, and we have a compact particle accelerator. Okay, so what we have here is, this is the design of a cyclotron. So cyclotron is made of Ds, so we call them Ds, and that's a proper word you can use in your writing when you write answers and these. So there are two Ds there. One is this, other is D, and these are hollow. So this here, that's this hollow here, and you can basically see from here that they are hollow here, and a magnetic field is set up which is perpendicular to this D. So basically what we have is, for example, we have a positive, we have not positive, let's not call it positive, we have a D, we have north pole here, and then we have a south pole at the bottom. So there is a magnetic field into the base here, which if I want to show, I can show it like this. All right. At the same diagram, if I take a top view here, this is the diagram that I'm looking at. I have these two Ds, and the magnetic field here is perpendicular to these Ds and into the base. And here what we have, what we call our ion source. Basically here we put a source of the particle that we want to speed up, we want to accelerate. And the thing that one thing I haven't shown is this is where your particle gets out, and you can get the particle from here. This is a basically escape kind of thing, escape vent kind of thing. So particles go here and they come back here. When they come to this size, they escape from here. We have a ion source here. So for example, suppose we launch a positive ion from here. So that positive ion goes there, and it's going with some velocity. The magnetic field is into the phase, so we can see that it will go in a circle because the particle is positive, the magnetic field is into the phase. We can see that it will go in a circle here, and because the velocity is small, so radius will be small. We already know that the radius of a particle moving in a magnetic field is mvr is equals to r equals to mv over qb. So because the initially velocity is small, so it will trace out a small circle here, small radius, and it will eject here. Okay, when it comes here, this particle comes into the gap, what we do is we change the polarity. There's a potential difference between these two D's. So let's call it D1 and D2. So what we do is when the particle comes back here, we make D1 positive with respect to D2. Sorry, other way around. We make D1 negative with respect to D2. So this particle is positive, it's coming here, and it gets attracted towards this negative D, and it goes there. It gets attracted, so when it's in the gap, it gains energy because there's a voltage difference, and its speed increases. So it enters the second D, this D1 here, it enters with a higher velocity. So the radius, higher velocity means the radius has increased a little bit. So it will trace out a slightly bigger circle this time. And when it comes back to the gap here, we change the polarity of D's. So this D here, instead of when D1 earlier, when particle came here, we made D1 negative. When it comes back here, we make D2 negative. So this positive particle feel a force of attraction towards this D2, second D here, because this D is now D2 is negative, and it again gains some energy. It basically goes across a voltage difference. This is negative, this plate is negative, and speed again increases a little bit, so it traces out a bigger circle. And that way it keep on going, and when finally its radius has increased enough, it escapes from here, and we have our accelerated particle here. Every time the particle is crossing the gap, it is getting accelerated. When it is in D, there is no change in velocity because there is no electric field in the D here. There is no negative terminal or negative D or negative something attracting the electron, attracting the particle. So here it will be same speed. When it comes here, it gets a jump of speed, and when it comes back here to the gap, it again gets a jump in the speed, and that way it will keep on going circle. And every time it crosses the gap, its speed increases. So it is getting energy in sort of injections of a small increment. All right, so let's look at some maths of cyclotron here. So this equation we are familiar with, R is equals to mv. Okay, so we are familiar with this equation, RV is equals to mv over qb. Now, one thing that may look tricky is the fact that how we change the polarity at the right moment. You would think that the velocity is increasing every time when it comes to the gap, so the time between switching over the polarity of these D's would be different, right? First time you switch after 1 second, for example. When next time it comes, the velocity is increased, so probably you have to switch at some different time. So you would assume that the rate at which the switching of polarity takes place here would be different. It would change with time as the as the particle goes around in circles. But we'll see that it is not like this. So let's look at this. This is our equation we are familiar with. So let's find the time it takes the particle to complete one circle. Right, so CRT is equals to one circle is 2 pi r, and divided by velocity, that will give you the time the particle would take to complete one round here in the cyclotron. R is given here, so this R will be replaced with this R here, so T is equals to 2 pi over V, and this is my R. I'll write my R here, and V cancels out, and what we have is 2 pi over QB. So if you 2 pi m over QB, so we see that the time it takes the particle to complete one circle does not depend on the radius, it does not depend on the velocity. It got m, which is basically, once you got your particle selected, then m of the particle, q of the particle are constant, and then b is a constant. We are not changing b, so we see that the time the particle takes to complete one circle around this cyclotron is constant. It's not changing, no matter where the particle is going. Actually, what is happening is, when the particle is going in a bigger radius, then its velocity is also increasing, right? And it increases by exactly same ratio, so that the time taken by the particle to remain is constant. Here, the particle going in a small radius, but the velocity is small. Here, the particle going in a bigger radius, but then the velocity is also higher. So the time it takes is essentially the same. And this is the time that it takes, that tells us how much we have to, after what time we have to change this. So this is the time taken for once to complete one circle. It means we have to change the polarity. We have to change polarity in t over 2 times, which basically then becomes pi m over qb, right? Because in one circle we have to change the polarity twice. In one circle, the particle crosses the gap twice, so we have to, and this is one circle basically. This is time for one circle, and in one circle that polarity has to be changed twice, which means we have to change every qm over pi b over qm. Other thing is, what actually is happening is that these Ds are connected to AC source, and that AC source has a frequency. So frequency of the AC source, F is equals to 1 upon T, so it will be QB over 2 pi m. That is the frequency of the AC source which is connected to the Ds. Okay, let's go back to, now let's find out the final energy of the particle when it emerges from the cyclotron. I think I will clean this because I want to keep the picture in view, and I want to write as well, so I'll clean this thing up. And sorry. Okay, so what we saw that we already, I'll write that equation again. R is equals to mv over qb. Now what this equation is telling is that there is a correspondence between r and v. For any particular radius, there is a particular velocity. When the radius is big, velocity is higher. When the radius is smaller, velocity is lower. So there is a one-to-one correspondence between r and v. So using this, we can find the velocity. We'll rearrange the equation when we want an expression for v. So we can get rid of this m from here by dividing by m, putting m in the denominator, but we do that on both the sides. And then I want to get rid of this qb, so multiply with qb, and I do that on both the sides. So that cancels out, and what I'm left with is v is equals to q br over m. Now this expression basically gives me velocity of my particle for any particular radius. If you got some particular radius here, I can calculate the velocity corresponding to that particular radius of the path of the cyclotron. Okay, when cyclotron is coming out of the, when particle is coming out of the cyclotron, it has this radius. Look in the diagram again here, it has that radius, right? And that is the radius of the cyclotron, so radius of the D. So let's say the radius of D is equals to R, right? So when does our particle come out with? Our particle comes out with a velocity which corresponds to this radius. The particle is in this radius here, and all we need to do is we need to find the velocity corresponding to this radius. So substitute this value in place of R in this expression, we get V, and that's the final velocity with which the particle would emerge, because that's the velocity when the radius of the path of the particle is capital R, big R here. So velocity, this is the final velocity, you can call it, let's call it VF, QBR divided by M. Right, so particle emerges with this velocity, so kinetic energy of the particle that we get from this cyclotron, is equals to half mvf square. So just substitute the value of Vf from here. Vf is equals to Q B R over M square. That gives me half Q square B square R square divided by M square, and M cancels out this like this. I got half Q square B square R square over M. So from our cyclotron we will get particles having this much kinetic energy. And here you can see that the voltage between the D's does not come into picture. There is no delta V here. There is no voltage here, voltage difference that's applied between the plates. What it means is that irrespective of the value of the delta V, irrespective of the voltage difference between D's when we are accelerating the particle in the gap, the kinetic energy will be this. So for example, my AC voltage here, this AC voltage here is 200 volt. Then also I'll get this energy, and that AC volt is 100 volt. Then also I'll get this energy, particle of this energy. How can that happen? When the voltage difference between D's is this much, particle is getting a bigger injection of energy. When it is 100 volt, then it is getting a smaller dose of energy every time it crosses the gap. But in both the cases, particle eventually ends up with this energy. So what is happening is, when it is 100 volts, the particle is crossing the gap many more times than it is crossing when it's 200 volt. Yeah, you final energy is same. If you give smaller doses, then you have to give many doses. If you are giving bigger dose, then you have to give less number of doses.